All right, we're going to be working in this set of notes, still in topic 6.1. We're going to be working towards the definition of the derivative from first principles, but we're going to start with this idea of secant lines and tangent lines. So secants touch the graph of a function at 2 points, tangent touches at 1 point. And this is a bit of a misnomer because if we have a function that curves back on itself like a cubic, then our tangent could end up touching at another point, but it's not necessarily a secant. So here, our secant would be PQ, and our tangent would be this line down here. And looking at PQ, I could calculate my slope. So in this case, my rise is going to be whatever the y values are at P and Q. So I could call that y2 minus y1 over x2 minus x1. But I see, of course, that x2 I've defined as x1 plus h. So that could be simplified to be y2 minus y1 over h. And so this is just some background with secants and tangents. Yeah? If we come into example 1 here, we've got an object moving along a straight line according to this function 5t squared. So of course 5t squared is a parabola, but we're not saying that the object is moving in the shape of a parabola. We're saying that our object is moving along a straight line. So our b value is the position relative to some fixed point. So if I think about my function, and here we have part of our curve, then in this function, what we're really saying is that this is our distance away from our initial starting point. So here would be our initial starting point. At 1, that's going to be 5 over here. When we've got 2, we're going to have a value up there of 20. So basically what we're saying is that after 2 seconds, we're 20 meters away from our fixed point. We're not moving in the shape of a parabola. So if I want to think about my speed at 1 second, then I want to bring my distance closer and closer. Because right now, if I think about putting in a line from here to here, oh, why does my function not always work? Let's try that again to put in a straight line. So if I calculated, if I drew in a secant and found this slope, I know of course speed is distance over time. So right now, the slope of this line is going to be, we've gone a distance of 15 meters over 1 second. So we might say that our speed is 15 meters per second. But we can see that we're getting faster as we move along. So our speed right at 1 is not actually 15 meters per second. So if we bring our second point closer to the 1, I'm going to get more and more accurate values for the speed. So that's what we're doing here. So if our h value is going to be the distance that we are away from this point that we care about, which is 1, then I can find new slopes. So my x2 value in this case would be 1.5. And now if I plug in 1.5 to my function, so then I'm going to have, let's make it easy on ourselves and clear all this out. So we've got 5x squared. And now I can take my table settings and, table settings, and change my independent variable to ask. So now if I go into my table, I want to figure out my y1 value at 1.5 seconds, and I get 11.25. So 11.25 minus 5 over 0.5. I could also come into my table and calculate that this way. So if I come back into y equals, I could do 5x squared minus 5 divided by, so my x value that I'm putting in is actually the x value plus h. So I'm going to subtract 1 off of that to get my correct denominator. So I can come back into my table, see that this calculated value is a speed of 12.5, so already slower than our 15. And then we can move closer and closer. So now I'm only 0.1 second away from 1. So I would have 1.1 here as my second value. And then I could say 1.1, and I get 10.5. And as you can see, it's like we're finding a limit. So let's skip down to my 1.001, and we get that it's approaching 10. Hopefully the same is going to be true when I approach from the negative side. So let's see. My x value now would be 1 minus 0.01. So we've got 0.99, and we can see that we end up with 9.95. So we are getting values that appear to be approaching 1 as we get closer towards creating a tangent. So the slope of this line, I could either try to calculate it based on what I see, and what I see is that I've gone up 5 over a distance of half a second. So our slope appears to be 10. Oops. Okay. So we've been using our calculator to help us figure this out. And what we've been doing is finding our delta y over delta x. So we abbreviate delta y as dy and delta x as dx. So this dy dx value is really our slope of the tangent. So dy dx is the slope of the tangent, at a specific point. Since I know my main function, I can actually calculate this. So let's go back into our calculator and let's quit. If I go into alpha f2, I see that I have n deriv. So I'm deriving a function. I can either type in my function, so I can use a's or x's, doesn't matter. I have 5x squared, and I want to find the derivative when x is 1, and I get that it's 10, which is what I had suspected based on looking at my table. But I can also find this with algebra and limits. So as we saw, we're bringing our points closer and closer together. So we want our limit to be approaching 0. So let's go ahead and calculate this out. So our f of x was 5x squared. So 1 plus h is going to be 5 times 1 plus h squared minus 5 times 1 squared all over h. We still have our limit, because right now, if I plugged in 0, I would have 0 over 0. We know that doesn't work. Now 5 times 1 plus 2h plus h squared minus 5 all over h. That's going to give me 10h plus 5h squared. The 5s are going to cancel. So limit as h goes to 0 of 10h plus 5h squared over h. Now my h's cancel. Limit as h goes to 0. I'm going to slide this down. limit as h goes to 0 of 10 plus 5h. Now I can evaluate, and that gives us 10, matching what we suspected. So in this case, we were using f of 1 because that was our certain point. We can come back and generalize that to call our x value a. So here our x was 1. That's where we wanted to evaluate at 1 second. But if we let x equal a, then our slope of the tangent at x equals a is going to be the limit as h approaches 0 of f of a plus h minus f of a. So think about it, y value shifted a little bit away from our point that we care about. Our x values are a plus h minus a, which leaves us with just h. So this limit definition is called first principles.